Hello. The article we're going to go over today is called Learning Classifiers from Only Positive and Unlabeled Data. This article from 2008 is basically the foundation for the subdomain of PU learning. It is concerned with a specific definition of a problem. You have a binary classifier to be learned, and where you usually have two sets of examples, one positive and one negative. In this case, you have a set of positive examples and a set of unlabeled examples, meaning that some of these unlabeled examples could be still positive and some of them are true negatives. In this article, they showed that a classifier trained on positive and unlabeled examples predicts probabilities that differ by only a constant factor from the true conditional probabilities of being positive. They discussed that such a result can be used in two different ways to learn a normal classifier from this non-traditional training set. And they show practical applications in real-world problems by considering the protein datasets. Notation-wise, in this article, consider that y is the true label, meaning that if y is 1, the example is truly positive. S is whether or not the example is labeled. If an example is labeled, it should definitely be positive. And if it is not labeled, it could be positive or it could be negative, meaning that in the case of knowing that S is 1, we know that Y is 1. We'll talk about this a little bit more, but this basically means that all of the examples that are labeled are selected randomly, uniformly from the set of positive examples. But if S is 0, then it could be a positive example or a negative one. Thus, in this problem, you have an incomplete set of positive examples and a set of unlabeled examples, meaning that the usual assumption, which is the availability of explicit negative examples, does not hold in this problem setting. The TCDB database is what they use as an example of a real-world problem that fits this definition. Again, you have X as a data point, Y is its true label, and S is whether or not you have it as a labeled example in your dataset. One assumption that is here is that the probability of an example being labeled while it is negative is 0. Now another work, mainly reference 21 in this article, considers a case control scenario in which you have two training sets. The first one is concerned with the cases where S is equal to 1, and in the second case, all of the possible data points are drawn. Now this has some limitations that will be discussed, but the important point is in this work, there is a single set assumption for the dataset. This means that the probability of an example being labeled can also be estimated, while in the two-set assumption, it cannot. Obviously, as usual, the goal is to learn this function f(x), which corresponds to the probability of an example being positive. This is a traditional problem. And in this paper, f is called a traditional probabilistic classifier. Here is an important assumption. The assumption is labeled positive examples are chosen completely randomly from all positive examples, meaning that if an example is positive, the probability that it is being labeled is the same regardless of what the content of X is. This is called the selected completely at random assumption, and it means if you consider it as like a probabilistic graphical model, if you have X and you know that X has a certain label, in this new labeling procedure that takes Y to S, given the value of Y, so if you know that the value of Y is something, S becomes d-separate from X, and it doesn't depend on it. So the probability of S being 1, given X, and Y being 1, doesn't depend on X. So we discussed that the probability of an example being labeled, given that X and Y equals 1, does not depend on X, so it becomes the same as this. Now let's call this C, meaning that C equals the probability of S being 1 conditioned on that Y is 1. Now consider GX being a non-traditional probabilistic classifier, meaning GX is trying to estimate the probability of S being 1 given X. The first thing I'm going to talk about is lemma 1 in this article. What this lemma says is that if you consider the probability of S equal 1 given X, given the assumption we had, we know that this is the same as this. We know that this second component is 0, so we have this. Now we use Bayes rule and things like that and get to this new equation. And we discussed this independence, this conditional independence. So we would have which is C times P. What this says is that if C is the probability of S being 1 given that Y is 1, P Y equal 1 given X is going to be 1 divided by C times P S equal 1 by X. Some important points from the paper. Although this result is simple, it had not been published before 2008, and it is not an obvious result, and had not been previously formalized. One consequence is that f is an increasing function of g, meaning that if the problem we are concerned with is a ranking problem, then g can be used directly instead of f. Another one is that f, meaning g divided by c, is a well-defined probability f less than or equal to 1 only if g is less than or equal to c. Now let us talk about estimating c. Consider you have a validation set V where cardinality of V is M. There's a subset P of this validation set in which examples are truly positive, and the cardinality of that subset is N. Note that we're trying to estimate this, and because of this component, let's say we focus on the subset P, and then the first estimator that we will propose would be 1 divided by N, and then basically integrating over these positive examples and value of gx. Noting that gx was an estimator of probability of S being 1 given X, and then N is basically the size of the subset P of positive examples that are a subset of V. It is fairly obvious to show that, meaning that given that gx was the probability of S equal 1 given X for all of the x's, it also holds for X as being member of this positive set P. So you can write this as this. Now this part becomes 0 because X is a member of P. And given that independence assumption, we will have this, which means that it's going to be C. Another estimator, let's call it E2, can be found this way. One thing to note here is that if you consider this expected value, this basically would be the same as saying which we'll get to this, the probability of the probability of S being 1, which of course is times M, the cardinality of V. The third possible estimator is the maximum value of gx on V. Now from these three, the E1 is better, both because it doesn't have the variance term introduced in the denominator, and also it doesn't depend on one example, and given the fact that it works based on aggregation, it is more reliable. So in practice, usually E1 is better. Now we want to talk about weighting unlabeled examples. Consider that you have a function h, which is a function of h, x and y, and you want to estimate the expected value of h on x and y, given that x comes from the distribution of this dataset, and you only have x and s examples. Based on the assumption that discussed before, you know that the probability of y being 1, given that x and s is 1, because if an x is labeled, then it is positive. Thus, we only need to consider the case in which s is unlabeled. To write this, we can expand it like this. Given the binary nature of this problem, you can write it this way. Note that this conditional independence that we discussed means that this part becomes 1 minus c. And we discussed that this is different from p of s equal 1 given x by basically dividing that by a factor of c. So let's divide that here. Now, on the denominator you have this, and on the denominator you have this. And this could have been estimated using G, which is a non-traditional classifier. Furthermore, we have a function x and y, and we have this distribution defined by x, y, and s. You can use the chain rule and write it this way. Probability of x, and then for s you will have this way, probability of an example being labeled, and then using that conditional information you can write it this way. So this is exactly the same as the one above, but you can now expand it and say for each example note that you don't need to consider the case of y equals 0 where s is 1, so this is the only term for the case of s being 1. But for the case of s being 0, you are concerned with this as well as this. Now, if you want to estimate this using an empirical average, you have your validation set V, which had the cardinality of M. So you can basically go through all examples and average this term. And the term is, for those that are labeled, you know that the value of y is 1. And for those that are unlabeled, the weight you associate with it being positive is Wx, and the weight you associate to it being negative is the complement of that. Note that you basically want to get from here to here and use this as a mechanism, as justification, so as to consider the positively labeled examples with the positive weight of 1, and then consider that unlabeled examples could be positive with a weight Wx and negative with a weight 1 minus Wx. And Wx, based on the equation above, is this function, which we derived to be this. And this could be estimated using GX, the non-traditional probabilistic classifier. The paper mentions that there are two ways in which this result can be used in order to modify a learning algorithm. The first method is to express the learning algorithm so that it uses the training set only via computation of averages and then to use the result above to estimate each one of these averages. This is the first method. The second method, which is nicer in my opinion, is to modify the learning algorithm so that training examples have individual weights. Meaning that for each unlabeled example, you have one copy which is positive with this probability, with this weight, and the other one is negative with this weight. Now, in the special case of considering that hx and y is y, you can use the results above to get to this, which is an important value. By plugging in essentially the values, you will get to the expected value of y. And note that y, this value, the expected value of y, can also be called the prevalence of y among x. An alternative method to estimate this is using the definition of C, which was P of S equals 1 given Y equals 1. So you can basically write it this way. And you know that based on this, by just multiplying both sides, you can get this. Now you know that the probability of an example being labeled and positive can be used, can use n divided by m as an estimator for it. So you can use that, and then you can use this estimator of C and get to this. One important difference in this single set assumption compared to the case control scenario, which was from this reference of this article, is that the probability of y equal 1, or that prevalence, cannot be computed in that case, but it can be computed in this case. Now, since all these arguments are about probabilities, they consider the classifiers that output correct probabilities, that are in other words called well calibrated. They try fitting a one-dimensional logistic regression function, which is often called Platt scaling, to the SVM classifier in order to obtain these calibrated results. Now they synthesize data, which is here, and the way they synthesize it is that they consider two-dimensional Gaussians, one for positive and one for negative. They have 500 positive data points, 1,000 negative data points, and they use 20% of these positives as positive set, and the rest is unlabeled. They find that the first estimator of C is a lot more accurate. In their application to the real-world data section, they focus on the SwissProt database. The main point in this page is to use the libSVM library. They have used Platt scaling to get probability estimates, and then they've adjusted them based on lemma 1. They first run Platt scaling, they get the probability estimates, they are converted to weights, and then they are used in the next run of the SVM. A lot more important details about this application is discussed in this page and the following. Looking at the true positive versus false positive curve here, we can see that the best result is associated with training on P union QQ being the subset of unlabeled sets identified by this algorithm as positive versus n. All in all, the central contribution of this article is lemma 1, which means that for the special case of positive examples being labeled at random, only a constant factor is what the difference mainly is about.